So, hello everyone. We'll be beginning with chapter 9, which is called the Stability of Equilibrium Buckling. And this is the last chapter and the last topic of our course, which is Mechanics of Solid uh, APL 104, which is towards the mechanical engineering students. Okay, so let's go through the introduction first. It says in the previous chapters we have investigated the configurations and stress distributions in systems which were in equilibrium. Okay, when they say we have discussed the configuration, that means the displacements, the strains, the stresses, distributions in the systems, in the sense how is the stress varying, how is the displacement varying, how are the strains varying in your systems. Okay, and they were all in equilibrium. That was the important part. All systems until now were in equilibrium. Okay, so we said that the system was in equilibrium if the forces on every subdivision were balanced. So you could apply the force balance and moment balance not just on the overall system but also internally. I mean, you would hypothetically make a cut and then include those so-called internal forces and moments, and now they would be external, and hence you could apply the force in the equilibrium balance. So that is what you could do. In this chapter, we shall widen the scope of our investigation by considering the behavior of systems when slightly disturbed from their equilibrium configuration. So this is what we do. We want to disturb this slightly. Until now we haven't done this. Okay, so, and we want to see what will be the behavior of systems when which are an original but you slightly disturb that equilibrium. So when the forces no longer balance within a system, there will be acceleration. I mean, we knew that, and in general a complicated resulting motion. We shall not attempt to obtain a complete picture of this motion, but we shall restrict our attention to the following question. When slightly disturbed from an equilibrium configuration, okay, does a system tend to return to its equilibrium position, or does it tend to depart even further? So this is about the configuration of a system. So the words are very careful, and that's why they have been italicized in your textbook. When slightly disturbed from equilibrium configuration, okay, does a system return to its equilibrium position back, in equilibrium configuration back, or does it tend to depart even further? Okay, so just take a particle physics example. You have 1, 2, 3 and 4 particles. Okay, they are in equilibrium. Okay, I mean, in the sense the forces, moments of this system are balanced. Now if you slightly disturb this system from this equilibrium position, in the sense take this one point to somewhere over here, will this new configuration is something, that new configuration, keep in mind, is not in equilibrium but slightly outside of equilibrium. So what should happen now? Will this system rearrange itself back into configuration, back into equilibrium, or will it become more away from equilibrium? Okay, so that is something which we have already seen earlier, and this is the example which I think is there. You consider a small weight on a frictionless surface. So this is a small weight on a frictionless surface. The forces on the particle are the gravity and the normal reaction of the surface are clearly in balance wherever the surface is horizontal. Okay, these balance positions are indicated by the letter O. Okay, you see O over here, they're always on balance. Okay, they say that now the forces on the particles are clearly balanced wherever the surface is horizontal. So over here the surface is not horizontal, and hence you would know that the forces will not balance out. Okay, and over here it is balanced. It is balanced because the surface is horizontal. Over here again the surface is horizontal over here but not over here. Okay, so these are the cases where you were at equilibrium. So just to tell you, O is the point where it is balanced in all the three diagrams. Okay, in this case O could have been anywhere else, but we are just taking one point where it's balanced. Now in figure 9.1a, okay, the weight is shown displaced slightly from its equilibrium position. So what we do now is we displace this slightly from its equilibrium position to this new position. The forces on it no longer balance, but the resultant unbalance is a restoring force. Okay. The resultant unbalance is a restoring force. It is restoring because it will try to bring it back to this position. Okay, that is, the particle is accelerated back. Remember, there will be acceleration, but this acceleration is to bring it back to equilibrium, or it is to bring it away from, or take it away from equilibrium. So in this case, it turns out the acceleration which the system will have, and the system will have the acceleration because it is not in equilibrium, is to bring it back towards the equilibrium position. And this, as you are aware, is called a stable equilibrium. Consider 9.1c. You have the opposite situation. Over here also you have the resultant unbalance, and this is a upsetting force, so it is not restoring but it is upsetting. That is, the acceleration now will be in this direction, which will take it away from the equilibrium position, and this is clearly unstable. In figure 9.1b, we have the borderline between the two previous cases. When the particle is displaced slightly from an equilibrium position, it is again in equilibrium, and there is no tendency either to return or to go further. Meaning, if you take it away from equilibrium, it continues to be horizontal, the surface, and it is a new so-called equilibrium. So this will not have any tendency either to go over here or to go over here. So this is called a neutral stability. Okay, so three situations we have already seen: stable, neutral, and unstable equilibrium. Now, by generalizing from the example above, we arrived at the following definition of stability of equilibrium. So this is what we want to study. A system is said to be in a state of stable equilibrium if for all possible geometrically admissible small displacements from the equilibrium configuration, restoring forces arise which tend to accelerate the system back towards the equilibrium. Please note the definitions very carefully. It says for all possible geometrically admissible small displacements. Here it was possible for this to go over here at this new position, but this was not geometrically admissible given the way we were in this problem. Okay, so it has to be either along this, either along this. Okay, so all possible geometrically admissible small displacements. Small is again important because you want to only slightly change the configuration, like this was only slightly moving on this side to disturb from equilibrium. Okay, restoring forces will now arise which tend to accelerate the system back towards equilibrium. Do remember, coming from this state back to equilibrium is through acceleration. In the sense, there is no equilibrium over here, no equilibrium over here, but equilibrium where at this point O. Okay, neither at this point there was equilibrium, nor in this path from this to this there will be equilibrium, this path. That is something you have to keep in mind, that your system so-called will be in acceleration when it wants to come back to equilibrium, in stable equilibrium. A load carrying structure which is in a state of unstable equilibrium is unreliable and hazardous. If you have, say, any structure, say a bridge, okay, something like this, okay. Now if you have any rod on this, say this one, which is in equilibrium, and due to any reason whatsoever you slightly disturb it, okay, it may be a very high wind, it may be a very huge mechanical shock or anything like that. Now if it is an unstable equilibrium, then this will deteriorate further and hence it will move away from equilibrium, and this entire system then will be able to break. Okay, it will be hazardous. So you try to look at the whole system perspective now. So let's change it back to this. Say this is the structure of a building, okay, and there are a lot of members, say a truss structure like that. So this whole structure has to be in stable equilibrium. Tomorrow if there is a small earthquake, for example, okay, then it will definitely move away from equilibrium, but since it has to be in stable equilibrium, it will develop restoring forces which will want to accelerate it back to equilibrium. So we want a stable equilibrium, not an unstable equilibrium. Okay, so let's now move to the next topic, which is elastic stability. So in figure 9.2a, AB is a rigid weightless bar. So let me just write it's a rigid weightless bar with a frictionless pin joint at B. So this is a frictionless pin joint, you know what it means, okay. When the bar is vertical, this is frictionless. If it was friction, then you would have some other treatment and you could approximate back to something else. Okay. When the bar is vertical, a horizontal force P can be applied at A. So you want to apply this horizontal force P at A, as in a 9.2A, or downward as in 9.2B. Okay. So you have these two ways of applying this force when it is originally vertical, like this and this. However, it is to see that a small rotation of AB will give rise to a restoring torque in A and upsetting torque in B. How do you see that? I mean, you can intuitively perhaps see this, okay? Or you can perhaps try to simulate something like this with a pen on your desk, okay? You hold it like this, and then you give a small rotation, okay? You give a small rotation of AB, and then you will see that this force P which you have will try to bring it back. So this is the rotation which you are giving, and then the restoring torque will be like this, and that is possible to see. I mean, this P is there, and then you have the arm of this force, so R cross B will try to pull it back. On the other hand, if you have this force like this and P like this, then this will actually become worse, in the sense it will go in this particular direction, so it will be upsetting torque over there. So these are the two examples where you can clearly see this, and it is a case of stable equilibrium. This is a case of unstable equilibrium. Now let's see this in terms of another example. So this unstable structure is what we want to see now, okay. Can be stabilized by adding a guy wires or transverse springs. So for this system B, if you put in springs like this, okay, then this will be stabilized. How would that happen? Now if you want to give a small rotation like this would be somewhere over here, and you would have P, Okay, what would be happening? This particular spring will try to pull it back, this particular spring will try to push it back, so it will have to go back over here. Okay, so it is sort of it is competing. So these two springs are trying to compete against the upsetting torque which would act in to destabilize it. Okay, so let's study how that happens. So in this one, you have a free body diagram to analyze the effect of small transverse displacement x. So what has happened is that this edge has moved x over here, and that means you have a small rotation which has happened. And this is small, that's the important part. So you can almost assume that this is going in vertically like this and not through an arc. Okay, not through an arc but horizontally. It's the movement of it horizontal. Reason being, this is small. I mean, we have seen that before. I mean, if it is small, then the arc can be replaced by a tangent. So this is the tangent. Anyways, so if x is that small displacement, transverse displacement, what are the spring forces which act in the horizontal direction? That will be kx plus kx. Okay, and then you will have you want to find the torque. That torque will be because of this lever L, so that will be 2kxl restoring. Okay, let me just write it like this. And the upsetting torque, okay, which is due to P, will be equal to Px. Okay, so that is upsetting. So this is just like R cross F. So this will be your force, this is your X, this will be P. Okay, so that is Px. So you have 2kxl which is restoring, Px as upsetting. Now you want to discuss the stability of this system for small deflections. I mean, the small word is always there. I mean, it has been there throughout. Okay. Small deflections. Now it depends which of them is larger. If the restoring is larger, in the sense Px is smaller than 2kxl, then you will have a stable equilibrium. If Px on the other hand, which is the upsetting, is larger than the restoring torque, then this will be unstable equilibrium. Okay, so this is fair enough, and you can see why these two conditions are there. Perhaps this is the first time we are dealing with inequalities, okay, uh, in so much of detail in this course at least. So I think you can go slowly about this, and this chapter will feel very different from the others because we were assumed to be in equilibrium in all those cases in the first 8 chapters of this book. So now we are slightly disturbing that. Okay, thus the springs have stabilized the strut for small loads P, but it is unstable for large loads P. If P is, in the sense, if X is not equal to 0, okay, so then it would all depend on how large P is. If P is small compared to 2KL, then you will have stable, and if P is large compared to 2KL, it would be unstable. So for small loads P, it can be stabilized, but it is still unstable for large loads. So if P is very large, and that you can intuitively also see. I mean, you can apply a really large force P, and then the springs will not be enough to bring it back to its equilibrium position. So what is the border line between P? P is equal to 2KL. Okay, since X is not equal to 0, and PKL is the border line. So this is the critical, or I don't know, whatever it's called, a critical or the buckling load. P smaller than this means stable, P greater than this is unstable. So this is called a critical load or buckling load. Now we'll look at a alternative method of seeing this problem. Okay. An alternative method of studying the structure which gives further insight into the stability problem is indicated in figure 9.4. So this is figure 9.4. Okay. Here we take the force P to be applied slightly off center. Look at this figure. P is not applied exactly on the center, this dashed line, as it was in the earlier cases. It is applied slightly off center. Okay. And the small distance epsilon is called the eccentricity. So this is the eccentricity of the load. Okay. So epsilon would be 0 if it was acting along the dashed line. Okay, the assumption of some eccentricity provides a useful model for many types of imperfections which occur in actual structures. That is, the bar might not be exactly straight, the springs might not be perfectly balanced. So why do we have this eccentricity? I mean, it's not necessary that the load will be uh, applying exactly on the center. It may be because we may not be able to achieve what exactly is shown on paper. Meaning, if the bar is not exactly straight, so if you are say you hold a pen on your desk and you try to upload a P force vertically, it is likely that this pen is not exactly vertically, it's not exactly perpendicular to the table. Okay, so there is an imperfection there. Similarly, the springs may not be perfectly balanced. I mean, the spring constants may be slightly different and so on. And this eccentricity which you now introduce in your system is taking care of all these errors which you are inadvertently including in your analysis. Okay, so this eccentricity is not just for having a, and I mean, you try your best to put your apply your load exactly in the center, but it may not happen for the reasons I have discussed. Okay, the bar for example may not be exactly vertical, or you may not be exactly able to apply this point at exact center of this. Okay, you may be slightly off, and the springs may not be balanced enough. Okay, so by their positioning or by their materials, whatever may be the case. So this is what the it accounts for imperfection, accounts for imperfections with respect to what is shown in the diagram to you and what exactly exists in a real life situation. Okay, so you want to now solve for the in transverse displacement x in the equilibrium position by balancing torques about B. So what you do is you take this small transverse displacement x. Okay, and this x is always measured with respect to the center. Okay, so the measurement of this axis, this x is with respect to the center, and then you would want to do the balance of moments. So let's see what that would be. If you want, so at critical condition, what would be the upsetting torque? That would be P into x plus E, x plus epsilon. And what would be the restoring torque? That would be 2kxl. Okay, so this is the critical condition at which the upsetting torque is equal to the restoring torque. So this would give us x is equal to epsilon p by 2kl minus p. The values of load P and transverse displacement X which satisfy 9.2, this is 9.2, okay, this was 9.1, So the values of p, okay, and x which satisfy this, p and x which satisfy 9.2 are plotted in figure 9.4c. So look at this 9.4c, x versus p, and the curve which you see over here is satisfying this equation, okay, this particular curve. The displacement are for small values of p, the displacement x is very small. So if you take p to be very small, okay, if p is very small, which is closer than 0, as you see the x will also be very small, something like this. And as p goes on increasing, then x will go on increasing. So that is the relationship which you see over here, okay. But when p is close to the critical value, okay, and what is critical? 2kl over here. So when p is close to this critical value, the displacement is large. So this line, horizontal line, is p critical, and at that point x becomes very large. You can see it by this particular curve, okay. So it becomes like this asymptotic sort of a behavior, and this is what it means. So physically, come back to see what it means. Physically, what it means, if p is around that critical point, then x will become very large. So you have to be careful around that p, okay. And that p is anyways because the distinguishing factor between stable and unstable equilibrium, okay. So that's an observation which is already made. Now what happens further? The dashed curve, this dashed curve which you see uh, in this figure, satisfies 9.2, okay, satisfies 9.2, and thus represents equilibrium positions, but these are for unstable equilibrium position. So this is somewhat of a mirror image of this one, okay, and it will satisfy this equation in the sense, if x is negative, okay, if x is small and negative, then p will be p will be of this value, okay. So p will be, if x is small, okay, I'm sorry, if x is, yeah, x is small and negative, then p will be like this, and above the critical point this will be like this. So over here you are in the stable region, over here you are in the unstable region, okay. So when we were discussing this, that as x becomes large, p will become larger, or as p becomes large, x will become larger, and near about the critical point x will be very large. So that was where it was still in the stable equilibrium, meaning the restoring force was still, I mean, the p was still greater than this particular thing, was still greater than this, and it was hence trying to pull it back. So, but on the other side, the reverse is true, okay. So if you come very close to the critical region, okay, if no, so sorry, if you are having a very small p over here, okay, let's consider this somewhere over here, then the x will keep on increasing, okay. On the other hand, if you have a p over here, then the x will keep on decreasing. So these are the two perhaps directions through which you can see this. So one of them is stable, the other of them is unstable equilibrium, okay. And you can see that one of them is trying to take you away from p critical, the other is trying to take you towards p critical, okay. This can be seen by considering figure 9.5. Let's see 9.5. which shows the configuration corresponding to point C in 9.4C. So C is where we are right now. Okay. So this is an unstable equilibrium and we want to see why it's unstable. So you have a negative x, meaning, if it was moving on this side, you have a positive x. So this side it was a positive x, this side was a negative. So it has moved by this distance minus x. The center has moved by this distance minus x. Okay. And this spring will now push it. So it will be kx. This will try to pull it. It will be kx. X is negative both cases. Okay. And which shows the configuration concept. Imagine a small disturbance of position which the strut moves to the left, that is x becomes more negative. According to figure 9.4c, a smaller value of p is required for balance in disturbed position. According to figure 9.4c, this one, a smaller value of p is required for balance in the disturbed position. So you, from x equal to 0, so this is x equal to 0. Okay, you have an x equal to minus x, some negative value. So you see the p required will be less. Okay, that is what they say. A smaller value of p is required for balance in the disturbed position. Since the load p is actually unchanged during the disturbance, okay, that was one thing which we had always taken along. The value of P was unchanged during the disturbance. The new position is one of unbalance, and the direction of the unbalance is such as to move the strut further from the original equilibrium configuration. So since the load P is actually unchanged during the disturbance, the new position is one of unbalance, and the direction of the unbalance is such as to move the strut further from the original equilibrium position. Whereas when P is greater than the critical load P critical, okay, in this entire region P is greater than P critical, the equilibrium positions for small x are unstable. Okay, that's what we have seen and known how the values will change. Okay, so now when P is less than the critical load, okay, let me just rub this part. When P is less than the critical load in this region, the equilibrium positions are stable. Furthermore, the equilibrium displacements are small if P is not too close to the critical load. For example, X is smaller than epsilon if P is smaller than half of P critical. The equilibrium displacements are small, X is small if P is not close to the critical load. So if you are somewhere over here, okay, then your equilibrium displacement is small. So X is small in this region, X is tending to 0 in this region. And that is happening roughly for a P which is smaller than P critical by half, somewhere over here, which is half the length of this entire region. The simple model of figure 9.4 is a good prototype for understanding the nature of elastic stability in more complicated cases. Okay, so in the ideal case in which the strut is exactly straight and the load is exactly centered, no transverse displacement is possible until the critical load is reached. So in an ideal case, when you have a bar like this and the load is exactly in the center, ideal case, no x until P becomes greater than equal to P critical. So you have to keep on increasing, and this is again something you can do. Take a pen, obviously not with the nib, okay, you can put the cover of the pen, put it on your desk and apply a load P. Okay, you will see that the pen will not fall, or nor it will have any displacements P. Okay, and if you keep on increasing the load, eventually you will have a critical, you will have to overcome a critical load for it to have a transverse displacement X. Okay. When a small imperfection is present, there is always a transverse displacement, but it remains small until the load approaches the critical load. Okay, that is something which you see over here. It remains small until the load approaches the critical load. The equilibrium requirement 9.2 results from balancing torques in the deformed configuration of 9.4b. This is something new. Remember, when you did this was the deformed configuration, this one. This is different than what you had done in the previous 8 chapters of this book. In the previous chapters, preceding chapters, we have always assumed that because of the deformation was small, the equilibrium requirements could be applied in the undeformed configuration. Generally, this is not acceptable if the system is elastically stable and not in the neighborhood of a critical load condition. Okay, so that was a very specialized assumption which you were taking. So if the loads are not far away from the critical load, then only that is okay. Otherwise, you must do your force and moments balance in the deformed configuration. And since we are learning about an instability over here, we must consider that particular point. Okay. So since we want to sort of study the stability of equilibrium itself, we will not risk assuming that the loads are not near the critical region. Okay, so we are, for example, we have to work in a domain which can be over here as well. This was fine, something like this, in which you could define the force and moment balance in the undeformed case if you were in this domain. But since you want to study this entire graph, it's always better to write the force and moment balance in the deformed configuration. Okay, so let's see a example of instability. There are many examples of instability, but let's start one by one. Okay, so we have this several instances of instability are described briefly to provide the cases, to provide the reader with a qualitative appreciation. We do not specialize in buckling over here, but we see a qualitative appreciation of this topic, meaning not a quantitative, in the sense you don't start plotting graphs, lots of graphs for the whole system, but you should definitely be able to visualize what is the problem happening. One of these cases will be studied in detail in section 9.4. I think that would be the bending or the twisting of the beam. Okay, we'll see that in the next one. Just because we have enough mathematics and enough physics and enough equations and about it so that we can study. The others we will just see it briefly. So take a thin, deep, each word is important, thin, deep cantilever beam. So the thinness is important. As long as the beam sections remain vertical, they resist the bending action of P very effectively. The deformation being of the type considered in chapter 8. Okay, as long as the beam sections remain vertical, they resist the bending action of P very effectively, and that we have already seen that in chapter 8. This is what happens for small values of P. So P has to be small for chapter 8 to work essentially. Now if P becomes large than the certain critical value, so we don't know what that critical value is in this case, but we know that there is some critical value of a system, in this case the cantilever beam. And if P is larger than that critical value, the vertical configuration becomes unstable. And a small disturbance such as an accidental side load or a tremor causes the beam to twist and bend sideward. So this is what happens. You have a twisting. You can see how the surfaces have twisted, and then it has also bent. So both of the things are happening provided P is greater than a certain critical value. So this is a case of buckling. Okay. So that's where we were, and thinness of the beam is definitely much required for this to happen. Okay, twisting and bending. Now in figure 9.7, you have a flexible column. Okay, you have a flexible The flexible column is shown subjected to vertical compressive load. For small values of P, the column remains straight and is compressed uniformly. For small values of P, the column remains straight and is compressed uniformly. You know that. I mean, if you take, say, a rubber tube like this, okay, for small values of P, it will be vertical and it will be compressed slightly uniformly. Now, if P becomes larger than a certain critical value, the vertical position of the beam becomes unstable. A small disturbance causes the column to bend out or buckle. So then you have, if P is large, thereafter a small disturbance of the beam will make the column bend out or buckle. So this is bending out or buckling. Okay. Okay, so you have now a somewhat similar situation is shown in figure 9.8a. This is 9.8. Okay. Okay, so what we have over here is a thin walled cylinder. Remember, we have learned so much about cylinders. So this is thin walled cylinder. Okay, so in your textbook, the example is given that of a beer can, but I think a soft drink can should also be enough to do this experiment. So this is subjected to a compressive load P, and for small values of P, the vertical walls remain cylindrical. Okay, you can take the drink out of the can and then do this. Okay, so for small values of P, the vertical walls remain cylindrical. So if you apply a small load P, it will be vertical, you know that, and will be compressed clearly. Now if P becomes too large, then this position becomes unstable, and you know that. I mean, you try to crush a can like this, you place it under your foot and then apply a large force. So that is where this crushing will happen, and a small disturbance causes the vertical walls to bend in and out and eventually to crumple. So this is crumple in a rather complicated pattern and is indicated in 9.8. So some parts you will know will go in, the others will come out. So this is called crumpling, and this is an unstable. After the instability is reached, a small force after that, a small disturbance after that, and then it will not be able to come back to equilibrium. On the other hand, it will move away from equilibrium. So this crumple zones is also used in design of cars, especially during crashing. So when a car wants to crash, I mean, it doesn't want to crash, but in a situation it does crash, there is a crumple zone, okay, which sort of protects the passengers inside. So you should learn about this crumple zone in a car from the internet. The important part is this, and I will repeat the reasoning one more. It's not that P keeps on becoming large and this happens. No, because it is not a load versus displacement graph which you are trying to draw. I mean, it's not elastic or a non-elastic thing. We are trying to learn where the equilibrium is no longer valid. So it is in equilibrium, okay. Now you keep on increasing P, it continues to be in equilibrium, but the compression is there. Perhaps you can have this linear relationship by that time. What happens is when this P becomes greater than equal to this P critical, or say equal to this P critical, we don't know what it is for this scan, but we know that there is a critical value. After this, any disturbance of any type, okay, either the tremor or a load or anything for that matter, will be enough for it to take it away from the equilibrium. So that is exactly what is happening. Please don't confuse this with trying to oversimplify the situation. Okay. Okay. So okay, so let's stop over here. The rest of the two cases and the flexible column we'll study in the next class. Okay, so let's leave it for over there, just so that we don't have to rush through anything towards the end. So thank you, and we'll see you in the next class.